Welcome to this coding problem walkthrough. Today, we'll explore problem number 1742, maximum number of balls in a box. This problem challenges us to think creatively about number manipulation and efficient data handling. Let's dive in and uncover the best strategies to solve it. In this problem, we are tasked with distributing balls into boxes based on the sum of their digits. Imagine we have balls numbered consecutively from a given low limit to high limit, both inclusive. Each ball is placed into a box determined by the sum of its digits. For example, if we consider ball number 321, the sum of its digits is 3 plus 2 plus 1, which equals 6. This means ball 321 would go into box 6. Our objective is to determine the maximum number of balls that any single box can hold after distributing all the balls. The input to the problem includes two integers, low limit, which represents the smallest numbered ball, and high limit, which represents the largest numbered ball. Both values are guaranteed to satisfy certain constraints, such as low limit being at least 1 and high limit being greater than or equal to low limit. The output will be a single integer representing the maximum number of balls in any one box after the distribution process is complete. To illustrate, consider the first example where low limit is 1 and high limit is 10. This means the balls are numbered 1 through 10. We calculate the digit sum for each ball, which determines the box it goes into. For instance, ball 1 has a digit sum of 1, so it goes into box 1. Ball 2 has a digit sum of 2, so it goes into box 2, and so on. When we reach ball 10, the digit sum is 1 plus 0, which equals 1, so it also goes into box 1. After distributing all the balls, we see that box 1 contains 2 balls, while all other boxes contain only 1 ball. Therefore, the maximum number of balls in any single box is 2. Now, let's look at another example where low limit is 5 and high limit is 15. Here, the balls are numbered from 5 through 15. We compute the digit sum for each ball to determine its box. For example, ball 5 goes into box 5, ball 6 goes into box 6, and ball 7 goes into box 7. This process continues up to ball 9, which goes into box 9. For ball 10, the digit sum is 1 plus 0, which equals 1, so it goes into box 1. Similarly, ball 11 has a digit sum of 1 plus 1, which equals 2, so it goes into box 2. Finally, ball 12 has a digit sum of 1 plus 2, which equals 3, so it goes into box 3. This pattern continues as we calculate the digit sums for the remaining balls in the range. Continuing with this example, ball 13 has a digit sum of 1 plus 3, which equals 4, so it goes into box 4. Ball 14 has a digit sum of 1 plus 4, which equals 5, so it joins ball 5 in box 5. Similarly, ball 15 has a digit sum of 1 plus 5, which equals 6, so it joins ball 6 in box 6. After distributing all the balls, we observe that box 5 and box 6 each contain 2 balls, which is the maximum in this case. Once again, the output is 2, as that's the highest number of balls in any single box. Now let's examine one more example where low limit is 19 and high limit is 28. Here, the balls are numbered from 19 through 28, and we calculate the digit sum for each ball. For ball 19, the digit sum is 1 plus 9, which equals 10, so it goes into box 10. Ball 20 has a digit sum of 2 plus 0, which equals 2, so it goes into box 2. Similarly, ball 21 has a digit sum of 2 plus 1, which equals 3, so it goes into box 3. Ball 22 has a digit sum of 2 plus 2, which equals 4, so it goes into box 4, and ball 23 has a digit sum of 2 plus 3, which equals 5, so it goes into box 5. This continues for the remaining balls in the range, with each being placed into its respective box based on the sum of its digits. To solve this problem efficiently, we can follow a systematic approach. First, iterate through each ball number from low limit to high limit. For each ball, calculate the sum of its digits to determine the corresponding box. Use a dictionary or an array to keep track of how many balls go into each box, incrementing the count for the appropriate box as you process each ball. Once all the balls have been distributed, find the maximum value in the dictionary or array, which represents the highest number of balls in any one box. This approach ensures that the solution is both accurate and computationally efficient, even for larger ranges of numbers. To tackle the problem of finding the maximum number of balls in a box, we considered two main approaches. First, we have the brute force approach. The intuition here is straightforward: iterate through all the balls, from the low limit to high limit. For each ball, calculate the sum of its digits, which determines the box number. Then, maintain a count of the balls in each box using a dictionary. Finally, you would scan through the dictionary to find the box with the maximum count. While this approach is easy to implement and understand, it can be inefficient when the range of numbers is large, as it involves dynamically managing keys in the dictionary. Now, the optimized approach builds upon key observations to improve efficiency. One observation is that the digit sum of a number can be calculated iteratively using modulo and division operations, making it proportional to the number of digits in the number. Another important insight is that the maximum possible digit sum depends on the length of the number. For instance, a 3-digit number like 999 has a maximum digit sum of 27. With these insights, we can shift from using a dictionary to a fixed size list, where each index directly represents a box number, reducing overhead and enabling faster operations. The optimized approach was chosen for its simplicity, clarity, and efficiency. Let's break it down step by step. First, we initialize a list called box_counts with a size large enough to cover all possible box numbers. For safety, this size can be set to 50, as even for large ranges, the maximum digit sum remains relatively small. In this list, each index corresponds to a box number, and the value at that index represents the count of balls in that box. Next, we iterate through all the balls, from low limit to high limit. For each ball, we calculate its digit sum, which determines the box number, and then increment the corresponding index in box_counts. Finally, we scan through the box_counts list to find the maximum value, which gives us the box with the highest number of balls. By using a fixed size list, this approach avoids the overhead of dynamically managing keys in a dictionary, which makes it not only faster but also more memory efficient. When comparing the brute force and optimized approaches, we can clearly see the trade-offs. While the brute force method is easy to implement, its reliance on dynamic dictionaries can make it less efficient for larger ranges, consuming more memory and introducing overhead. On the other hand, the optimized approach uses a fixed size list, ensuring predictable memory usage. This list-based approach is particularly advantageous because the size of box_counts is determined by the maximum possible digit sum, which is small and fixed regardless of the range of numbers. In terms of complexity, both approaches share a time complexity of O(n*(d), where n is the total number of balls and d is the average number of digits per ball. However, the optimized approach benefits from lower constant factors due to its simpler operations. Space complexity is another area where the optimized method excels, with a fixed O(m), where m is the maximum possible digit sum. Ultimately, the optimized approach strikes the best balance between simplicity, efficiency, and clarity. It avoids unnecessary dynamic memory allocation, ensures predictable performance, and is well suited for both competitive programming and real-world applications. In this problem, we are tasked with distributing a range of ball numbers, from low limit to high limit, into boxes. Each box is determined by the sum of the digits of a ball's number. Our objective is to calculate the maximum number of balls that can fit into any single box. To solve this efficiently, we first initialize a dictionary. The dictionary will store the box numbers as keys, which are derived from the sum of digits, and the values will represent the count of balls in each box. This choice is intentional because dictionaries in Python allow for fast and efficient insert and update operations, typically in constant time. Next, we iterate over all the ball numbers in the specified range. For each number, we calculate the sum of its digits, which will serve as the box number. This sum of digits is the key idea that helps us group balls into their respective boxes. Calculating the digit sum is straightforward and forms the foundation for the next steps in the algorithm. To calculate the sum of the digits of a number, we initialize a variable digit_sum to 0. Then, we repeatedly extract the last digit of the number using the modulus operation, number%10, and add it to digit_sum. After adding the digit, we remove it from the number by performing integer division, number // equals 10. This process continues until the number becomes 0. Once the digit sum is calculated, we update the dictionary. If the box number already exists as a key in the dictionary, we simply increment its count by 1. Otherwise, we add the box number as a new key and set its value to 1. After processing all the ball numbers, we iterate through the dictionary to find the maximum count of balls in any single box. This maximum value is the result that we return. These steps ensure that we efficiently compute the desired outcome while minimizing unnecessary computations. An important insight here is that the maximum possible box number is determined by the sum of the digits of high limit. For instance, if high limit is 9,999, the largest box number would be 36, which is the sum of 9 plus 9 plus 9 plus 9. This observation limits the size of the dictionary, making the algorithm space efficient. The dictionary serves as the core data structure, mapping box numbers to their respective ball counts and allowing both updates and lookups in constant time on average. In terms of time complexity, calculating the digit sum for a single number takes O log 10 k, where k is the number itself. Since we process all numbers in the range from low limit to high limit, the total complexity is O n asterisk log 10 k, where n is the number of balls. The space complexity is proportional to the number of unique box numbers, which is at most the sum of digits of high limit. This ensures the algorithm can handle large ranges effectively. Edge cases include scenarios like having only one ball, where the result is naturally 1, or when all numbers fall into the same box, resulting in the count of balls as the output. To better understand the algorithm, let's walk through an example. Suppose the input is low limit equals 1 and high limit equals 10. Here, the ball numbers range from 1 to 10. For each number, we calculate the box number by summing its digits. For instance, the number 1 goes into box 1, 2 into box 2, and so on. However, the number 10 has a digit sum of 1, so it also goes into box 1. As a result, box 1 ends up with 2 balls, while boxes 2 through 9 each contain 1 ball. The dictionary we construct looks like this: 1, 2, 2, 1, 3, 1, 9, 1. The maximum count of balls in any single box is 2, so the output is 2. This example demonstrates how the algorithm efficiently calculates the result by iterating through the range and grouping numbers based on their digit sums. The provided Python code snippet implements these steps, including the loop to calculate the digit sum and update the dictionary. Finally, after updating the dictionary with all the ball counts, we compute the maximum value using the max function applied to the dictionary values. This gives us the highest count of balls in any single box. In the code, if the sum of digits, or box number, is already present in the dictionary, its count is incremented by 1. Otherwise, a new entry is added with an initial count of 1. Once all numbers in the range have been processed, the max function is used to determine the box with the highest count. The result is printed, which in this example is 2. This straightforward implementation highlights the efficiency of the algorithm, both in terms of computation and memory usage, making it suitable for handling even large input ranges. This solution uses a dictionary to count the number of balls placed in each box, where the box number is determined by the sum of the digits of the ball number. First, we initialize a default dict with an integer default type. This allows us to increment counts without having to explicitly check if a key exists. Next, we iterate through all ball numbers from low limit to high limit, inclusive. For each ball, we calculate its box number by summing the digits of the number. To do this efficiently, we convert the ball number to a string, split it into individual digits, and use a generator expression to calculate the sum. Once the box number is determined, we increment its count in the dictionary. This operation is O(1) due to the efficient hash table implementation of Python dictionaries. Finally, after processing all ball numbers, we use the max function to find the highest value in the dictionary, which corresponds to the maximum number of balls in any box. This ensures we achieve the desired result efficiently, with a time complexity of approximately n*d, where n is the range size and d is the average number of digits in the ball numbers. This implementation handles edge cases such as small ranges, e.g., low limit equals high limit, and large ranges with varying digit sums seamlessly due to its algorithmic efficiency and use of Python's built-in data structures. Here, we begin by importing the necessary Java utilities and defining our solution class. The countBalls method takes two integers, low limit and high limit, representing the range of ball numbers. Inside, we initialize a hash map called boxCounts to keep track of how many balls each box contains, where the key is the box number and the value is the count of balls in that box. Next, we loop through each ball number within the given range. For each ball, the sum of its digits is calculated using a helper method called getDigitSum. This sum determines the box number where the ball will be placed. We then update the count for this box in the boxCounts map, using the getOrDefault method to handle cases where the box number doesn't yet exist in the map. Finally, we iterate through the values in boxCounts to find the maximum count, which represents the highest number of balls in any single box. This value is stored in the maxBalls variable and returned as the result. The helper method getDigitSum calculates the sum of the digits for a given integer. This method takes the input number, and initializes a variable sum to 0. Using a while loop, it repeatedly extracts the last digit of the number by calculating number %10, adds the digit to the sum, and then removes the last digit by performing integer division with 10. The loop continues until there are no digits left in the number. Once the loop completes, the method returns the total sum of the digits. This helper method is crucial for determining the box number for each ball based on the sum of its digits, ensuring that the logic in the main countBalls method operates correctly. To solve this problem, we start with the given range, where low limit is 1 and high limit is 10. Our goal is to determine how many balls end up in each box based on the sum of their digits, and then find the box with the maximum number of balls. First, we initialize a default dict called box_counts to store the count of balls for each box. Initially, this dictionary is empty. Next, we iterate over all numbers from 1 to 10. For each number, we calculate the sum of its digits. For instance, for ball 1, the sum of its digits is 1, so we increment the count for box 1. For ball 2, the sum is 2, so we increment the count for box 2, and so on. When we reach ball 10, the sum of its digits is 1 plus 0, which equals 1, so we increment the count for box 1 again, bringing its total count to 2. By the end of this step, we have processed all the numbers in the range and updated the counts for each box accordingly. After completing the iteration, we observe that our final box_counts dictionary contains the following counts: box 1 has 2 balls, while boxes 2 through 9 each have 1 ball. To determine the result, we find the maximum count among all boxes, which here is 2. So, the output for this example is 2. Now, let's consider another example where low limit is 5 and high limit is 15. We follow the same process, initialize a default dict for boxCounts and iterate over all the numbers in the range. Starting with ball 5, the sum of its digits is 5, so we increment the count for box 5 to 1. For ball 6, the sum is 6, so we increment the count for box 6 to 1. This pattern continues for balls 7, 8, and 9, where we increment their respective boxes to 1. When we get to ball 10, the sum of its digits is 1, so we increment the count for box 1. For ball 11, the sum is 1 plus 1, or 2, so we increment the count for box 2. Similarly, for ball 12, the sum is 1 plus 2, or 3, so box 3 gets increment. This continues until ball 15, where the sum is 1 plus 5, or 6, and box 6 gets increment again, bringing its total count to 2. At the end of this step, the box_counts dictionary shows that boxes 5 and 6 each have 2 balls, while the other boxes have counts of 1 or 0. In this case, the maximum count among all boxes is again 2, so the output is 2. Now, let's analyze a third example where low limit is 19 and high limit is 28. The process remains the same. We initialize box_counts as an empty default dict and iterate through the numbers in the given range. For ball 19, the sum of its digits is 1 plus 9, or 10, so we increment the count for box 10 to 1. For ball 20, the sum is 2 plus 0, or 2, so we increment the count for box 2. This pattern continues for balls 21 through 28. For instance, ball 28 has a digit sum of 2 plus 8, or 10, so we increment the count for box 10 again, bringing its total to 2. By the end of this step, we've calculated the counts for all boxes in the range. The final box_counts dictionary for this example is as follows: box 10 has 2 balls, while boxes 2 through 9 each have 1 ball. To determine the result, we find the maximum count, which is 2. Therefore, the output for this example is also 2. This approach of iterating through the range, calculating the digit sums, and tracking the counts in a dictionary allows us to efficiently solve the problem for any given range of ball numbers. To determine the time complexity of our solution, we start by analyzing the process of iterating through all the numbers between low limit and high limit. This loop runs for every number in the range, which means the number of iterations is equal to n, where n is calculated as high limit, low limit plus 1. This gives us an O(n) contribution to the time complexity. Next, we look at how the sum of digits is calculated for each number. This involves converting the number to a string, iterating through its digits, and summing them. The time it takes to sum the digits of a single number depends on the number of digits, which is proportional to log 10 of the number. Since the largest possible number in our range is high limit, the digit count can be approximated as O log high limit. When we sum the digits for all numbers in the range, the total contribution is O(n) log high limit. Together, these two components make up the primary factors in the time complexity calculation so far. Now, let's examine the time complexity contribution from updating the dictionary. Each time we calculate a box number, we update its count within the dictionary. Since a dictionary update operation is O(1), doing this for all n numbers in the range contributes O(n) to the time complexity. After processing all numbers, we need to determine the maximum value in the dictionary, where the keys represent unique box numbers. The number of unique keys in the dictionary is limited by the sum of the digits of the largest number, which is bounded by 9 log 10 high limit. Iterating through these keys to find the maximum count takes k, where k is the number of unique keys. Because k is constrained by O log high limit, this adds a minor overhead of O log high limit. Combining all these steps, the overall time complexity of our solution is O(n) log high limit, where n represents the size of the range between low limit and high limit. Switching to the space complexity, the primary factor is the storage required for the dictionary, which keeps track of the counts for each unique box number. The number of unique keys in the dictionary is determined by the sum of digits of numbers in the range. Since the sum of digits cannot exceed 9 log 10 high limit, the dictionary uses O log high limit space. Additionally, temporary variables contribute to the space requirements. For example, converting a number to a string and summing its digits requires space proportional to the number of digits, which is O log high limit. Other variables, such as those used for tracking the current number or box number, require constant space, or O(1). When we combine these factors, the overall space complexity of the solution is O log high limit. Let's compare this optimized solution to a naive approach. A straightforward method might involve explicitly simulating all box assignments and manually counting the occurrences. While it would still require O(n) log high limit time to compute the sum of digits for all numbers, it would likely involve additional overhead due to less efficient counting mechanisms. In contrast, the optimized solution avoids unnecessary intermediate computations and leverages a dictionary for efficient counting, achieving the same asymptotic time and space complexity but with improved performance. Now, considering best, average, and worst-case scenarios, the algorithm processes all numbers in the range and calculates the sum of digits for each one in every case. This means the time and space complexities remain consistent at O(n) log high limit for time and O log high limit for space, regardless of the specific values of low limit and high limit. Finally, let's solidify our understanding with a mathematical proof of the big O complexity. For each number, or ball, in the range, calculating the sum of its digits involves O log high limit operations, as the number of digits depends on the logarithm of the largest number. Processing all n balls in the range results in a time complexity of O(n) log high limit. As for the dictionary, it contains at most O log high limit unique keys. Iterating through these keys to find the maximum count is an O log high limit operation, but this is dominated by the O(n) log high limit contribution from summing digits. Thus, the overall time complexity is O(n) log high limit. For space complexity, the dictionary and temporary variables together require O log high limit space, confirming the final complexity of O(n) log high limit for time and O log high limit for space. When tackling this problem, it's important to be aware of some common mistakes that can trip you up. First, ignoring edge cases is a frequent issue. For example, when low limit equals high limit, or when all box numbers end up being the same, it's easy to overlook these scenarios during testing. Make sure your solution works for both the smallest and largest possible inputs. Next, improper handling of box numbers can lead to serious issues. If variations of the problem allow negative numbers, failing to calculate the digit sum correctly can result in errors. This is why your digit sum logic needs to be robust and carefully tested. Additionally, the choice of data structure is crucial. Using a list instead of a hash map or dictionary to track box counts can slow your solution down significantly, as hash-based structures enable faster lookups and updates. Another common pitfall is overlooked constraints. Assuming input ranges are smaller than they actually are can lead to solutions that don't scale well. Always verify the constraints and optimize your approach accordingly. Finally, avoid hard-coding values for box ranges or limits. Instead, dynamically derive these values based on the inputs to ensure your solution handles edge cases gracefully. Now, let's discuss some insights that can help you perform well in interviews when solving problems like this one. Digit sum calculations, as seen in this problem, are a common theme in technical interviews. One way to improve efficiency is to pre-compute digit sum values whenever possible, which helps you avoid redundant calculations. Another key takeaway from this problem is the use of hashing patterns. Leveraging hash maps or dictionaries to group and count items efficiently is a critical technique that applies to many problems beyond this one. Interviewers also appreciate it when candidates can articulate the trade-offs between different approaches, such as brute force versus optimized solutions. For example, reducing the number of iterations or pre-computing results can significantly improve performance. Additionally, always stress the importance of constraints during your discussion. Clarify any ambiguities, and ensure your solution accounts for edge cases and large inputs. To build a broader understanding, you might want to explore related problems. For instance, LeetCode 169, majority element, involves finding the most frequent element, which is similar in its counting mechanism. LeetCode 1365, how many numbers are smaller than the current number, employs a different grouping technique but shares the counting theme. LeetCode 202, happy number, applies digit sum logic in a different context, and LeetCode 128, longest consecutive sequence, focuses on grouping elements efficiently using hashing. Studying these problems will deepen your understanding of these patterns. Let's now explore some alternative approaches to solving this problem, starting with the brute force method. Here, you iterate over all numbers within the range, calculate the digit sum for each one, and update the box counts accordingly. This approach is straightforward, but it's inefficient for larger ranges due to its time complexity of O, n asterisk m, where n is the size of the range and m is the average number of digits per number. A more efficient solution involves optimized digit sum calculations. Instead of recalculating the digit sum from scratch for every number, you can use a rolling sum approach. For example, as you move from one number to the next, you incrementally update the digit sum, which reduces redundant calculations. This approach achieves a complexity of O, n asterisk k, where k is a constant factor related to digit calculation. Another advanced technique is pre-computing and caching results. Here, you pre-compute digit sum values for all possible numbers within a reasonable range, say, 1 to 100,000, and reuse these values during the main computation. While this reduces redundant calculations significantly, it does require additional memory. In summary, solving digit sum-based problems effectively requires a focus on correctness, efficiency, and robustness. Always handle edge cases carefully, leverage hash maps for efficient counting, and remain prepared to discuss the trade-offs of your approach during interviews. Great job reaching the end of this problem. Today, we covered the maximum number of balls in a box problem, learning how to apply efficient data structures like hash maps to solve it. Keep practicing similar problems to sharpen your skills, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!